Welcome everyone to our fourth lesson in Unit 3. Today's lesson is going to be on gas laws. We're going to be investigating a few different gas laws, and by the end of the lesson you should be able to use those gas laws to solve different problems. Now the image that we see here with this person floating with a bunch of balloons, each of these gas laws that we'll learn about today is an act here in this image. As these balloons rise from the ground up through the atmosphere, we have changes in the pressure of the balloons, in the temperature of the gas inside and around the balloon, and actually the volume of the balloon, which means the sizes of the balloons are going to change as they rise from the surface of the earth up through the atmosphere. And there was a video recently, a special that was aired on YouTube, David Blaine's Ascension. I have a link to it here, and I encourage you to watch it. It is kind of like a little movie documentary, but he goes through kind of the science behind his ascension. He had a rig set up with balloons like you see in the picture here, and he rode them a few, I think it was maybe around 30,000 feet or so into the atmosphere, and then jumped from his balloon rig and skydived back down to the ground. And he explains in there several of the different gas laws and how they were going to come into effect during this ascension. So if you get a chance, I encourage you to check that out. So today we're going to be taking a look at 4 different gas laws, and they deal with relationships between temperature, pressure, and volume of a gas, indicated by a capital T, a capital P, and a capital V. And these gas laws are going to be used to determine how changing one variable is going to affect the others. Now, when we're talking about pressure, we're going to be using, or we'll come across 2 different units of pressure, atmospheres and kilopascals. And both these are listed on Table A in your reference table. Volumes of gas, we're going to see units in milliliters and liters. And temperature, we're going to see some in Celsius, but what we're going to have to do is we're going to have to convert those to the Kelvin scale by adding or subtracting 273, depending which direction we're going there. Now, the gas laws are based on Avogadro's hypothesis, which we learned in the last topic, which said that equal volumes of gases at the same temperature and pressure are going to contain the same numbers of molecules. Now, STP, which is standard temperature and pressure, does not mean the same mass. So we want to make sure that we're clear on that. Standard temperature and pressure doesn't mean that we have the same mass of gas. Now, for each of these types of problems we're going to see, I'd like you to follow a 5 easy step process, which is how we approach most of our problems in this class. First, we want to get rid of the words and make a little table. And this is what I would call defining variables. So you want to define your variables, whether that's individually or in a little table. Make sure you write your equation down. In that equation, circle the variable that we're trying to solve for based off of information given in the question. The second part here, rearranging the equation, I'll leave this up to you if this is a step that you like to do. I tend to not rearrange the equation, but it can be easier if you do it before you start plugging in numbers. So then we'll plug in our numbers on paper and then into the calculator, making sure that we're using the right operation. And we'll run our answer using sig figs. Now, the first law that we'll take a look at is Boyle's law. And Boyle's law relates pressure and volume of a gas. And the law states that an increase in pressure leads to a decrease in volume. And the key point here is that this is an inverse relationship. And it says that the product of the initial pressure and initial volume of the gas has to equal the product of the ending pressure and volume of the gas. And we see our inverse relationship graph between pressure and volume here. And before we get to our practice, I'll show you a quick example of what Boyle's law means. So on here, we have a closed container and we can hold some things constant. We can keep nothing constant. We can change the types of particles and a few other things. We're only going to use one type of particle for now. So I'm going to pump in some gas into this closed container. As soon as we get gas in here, we see pressure forming. And we saw temperature. We didn't see temperature before. So now that we have moving particles, we have a measurement of that kinetic energy in our thermometer. We have a temperature of 300 Kelvin. And now we have pressure in the container. This pressure is caused by the collisions of these gas molecules or atoms with the walls of the container. Now, we can change a few things here. We can change the temperature, we can change the volume, and corresponding to that is a change in pressure. Now, Boyle's law says that a change in volume is going to cause a change in pressure, and that's an inverse relationship. So we're going to hold, if we're talking about a change between pressure and volume, we're going to hold temperature constant. And we're going to see what happens if we decrease our volume. Since we have an inverse relationship with Boyle's law, if we decrease our volume, we should see an increase in pressure. Let's see what happens. We'll go about half. Pressure goes from 12 atmospheres to 22 atmospheres. We have an increase in pressure. Why? Well, we took the same amount of gas that had a larger space, crammed it into a smaller space, and now we have a higher frequency of collisions on the walls of our container, which increases our pressure. The number of collisions and what influences that is going to have the greatest factor on our pressure. Now, if we go back to about the size that we were, and we increase the volume, we should see a decrease in pressure. And we see a decrease down to about 8 atmospheres. So that's our relationship with Boyle's law, an inverse relationship between pressure and volume. Now we'll do a couple example problems with each law so you guys can see what you're going to be responsible for, what you have to do with this topic. And we're going to follow that 5-step process that we went over a few moments ago. Now we have a sample of gas that occupies a volume of 2 liters at STP. Remember, STP is standard temperature and pressure. We can find those values on table A. If the pressure is increased to 2 atmospheres at a constant temperature, what is the new volume of the gas? Now when you're doing these types of problems, right now it might be a little bit straightforward, but on a assessment, it might be a little less straightforward. So you want to look for words in the problem that are going to indicate to you that we're dealing with a gas law. And when you see things like gas, volume, pressure, temperature, again, we see gas, or any changes like that, we see units of atmospheres, liters. STP can be a good indicator. We want to think gas laws. And the first thing that we want to do is define what we have. So using the units that we have in the problem, let's determine initial starting conditions and ending conditions of our gas. Now the sample of gas occupies an initial volume of 2.00 liters. We have 3 sig figs there. We want to keep track of this. The initial pressure, they don't tell us what it is, but they tell us that it's at STP. So that's standard pressure. In this case, we're going to use atmospheres. We could also use kPa. Atmospheres tend to give us a little nicer number. We know that the pressure changes, it doubles up to 2 atmospheres, and we're going to solve for the new volume of the gas. And here's our equation that we're going to use. So we plug our numbers into here, keeping our significant figures. And our new pressure changes to 2 atmospheres. And we're going to solve for our V2. We can call that X or V2 or whatever you'd like there. And our volume, after we plug in there and isolate the V2, comes out to a new volume of 1.00 liters. So we saw a 100% increase in our pressure, and we saw our volume get cut in half. So that holds true with our inverse relationship. On this next one, feel free to pause the video and attempt the problem and check your work. Now, first thing we're going to want to do is read the question and figure out if this is a gas law problem. So if a sample of gas occupies a volume of 1.5 liters at STP, if the pressure is increased to 2.5 atmospheres at a constant temperature, what is the new volume of the gas? So using Boyle's law, let's see if we can determine a new volume of gas, which would be V2. We don't know what V2 is, so let's define the rest. Our initial pressure is STP. So I'm going to use 1 atmosphere from table A. That's 1.00 atmospheres. The initial volume, V1, is 1.50 liters, volume indicated by the liter there. And the pressure's increased to 2.5 atmospheres. And we're going to solve for our V2. So we plug each of our unknowns into here. I'm going to leave the equation as is, as opposed to rearranging. If you did rearrange, what you'd end up with would be this equation. And then we could just plug in and solve for the V2, which, since I have it written there, I'm just going to leave it as is. So we'll plug in 1 atmosphere for starting condition, 1.50 liters, over our changed pressure, 2.50 atmospheres. That's going to be our V2. Atmospheres will cancel. We divide, multiply, and we get a V2 that's equal to 0.600 liters. That's a V2 there, making a little smudge. And it's 3 significant figures because each of our starting numbers here had 3 as well. The next law that we will investigate here is Charles's law. Charles's law deals with the relationship between volume and temperature of a gas, and it states that an increase in temperature leads to an increase in volume, and this is a direct relationship. And if you think of that, how warm air takes up more space than cold air. Cold air is much more dense. The gas is moving slower. It's able to stay a little bit closer together because it is lower energy. And when that gas warms up, higher energy, it takes up more space. And the equation that we'll see with this is V1 over T1 equals V2 over T2. And you can see from the graph here that this results in a direct relationship. So an increase in temperature leads to an increase in volume of a gas and vice versa. And we'll take a look at what this looks like with the simulator. I'm going to reset this. I'll pump in 100 particles, well, close to it, and put 100 in there. And Charles' law relates volume and temperature. So we're going to have to keep our pressure constant. We're going to have to do this in a couple different ways to kind of simulate this, and I'll show you what both mean here. So we're going to hold our pressure constant in relation to the volume of the container. Now, if we increase the temperature of the gas, if we hold pressure constant in relation to the volume, if we add heat to this gas, we increase the temperature, Charles' law says that the volume should increase as well. And since we want to hold the pressure constant, this box is going to adjust to try and maintain the same pressure, which means it's going to try and maintain a similar amount of collisions. Now, as we add heat to here and we give more energy to these molecules, they're going to want to hit the walls of the container more. So to compensate for that, the volume increases to try and maintain the same pressure. Now, if we were to cool that gas and we slow down those gas molecules, we're going to put them into a smaller area. We decrease the temperature, we decrease the volume to try and maintain that same amount of collisions. Now, if we switch this, I'm going to reset this. We'll put the gas back in there. And we'll change this. Now we can adjust. We're going to hold pressure constant in regards to temperature. So now as we change the volume of this container, if we decrease the volume, we're going to see a corresponding change in temperature. Again, we're trying to maintain that same pressure. So if we decrease the volume of the gas to move around to maintain the same number of collisions or the same pressure, we have to put them into a smaller area. And on the contrary, if we increase the volume, the temperature is going to change from 152 K and it's going to increase. And again, that's to maintain the same pressure. So we see a direct relationship between the change in volume and temperature of the gas. Now we'll take a look at a couple practice problems. A sample of gas occupies a volume of 5.00 liters at 300 Kelvin. If the temperature is doubled under constant pressure, what will the volume of the new gas be? First thing we do here is define what we have. We know the initial volume of 5 liters, an initial temperature of 300 Kelvin. Temperature gets doubled up to 600 Kelvin, and we're going to find that new volume of the gas. We're going to use Charles's law to do that. Now when we plug this in, we get 5.00 liters over 300 Kelvin, maintaining significant figures, and we set that equal to the V2 or the X over 600 Kelvin. And when we punch these numbers in, we cross multiply. What we end up with is a V2 that is doubled in size to 10 liters. So we see an increase in temperature, which leads to an increase in the volume. And that is direct. So temperature doubles, so we see the volume double as well. Now with this practice problem, feel free to stop the video, attempt it, and check your work. We have a sample of gas occupying a volume of 2.5 liters at 200 Kelvin. If the temperature increases to 300 Kelvin at constant pressure, what's going to happen to the volume of the gas? So we're going to solve for that new volume of the gas, which is our V2. We don't know what that is. We know that we want to use Charles' law to solve for this problem. So we need those other three variables. So we need a V1, we need a T1, and we need a T2. Now from the problem, we see that the gas initially occupies a volume of 2.5 liters at 200 Kelvin, maintaining significant figures there with the decimal. Pressure, or the temperature, increases to 300 Kelvin. Pressure does not change. What is the new volume of the gas? And we'll plug this in. I'm going to plug it in as is. This is 200 Kelvin. And we get a V2 over a new temperature of 300 Kelvin. When we cross multiply, we end up with a new volume of 3.75 liters, maintaining significant figures with 3. So we saw the temperature increase and a corresponding equal percentage of 33% increase on top of the initial volume, which increased to 3.75 liters. The next law we'll take a look at is Gay-Lussac's law. Gay-Lussac's law deals with the relationship between the temperature and pressure of a gas, where we see that an increase in temperature causes an increase in pressure. And this is a direct relationship similar to Charles' law. And if you think about this one, an increase in pressure means that we have more collisions between gas particles. And if we increase the temperature, then we're giving all of those gas particles more energy to move, which means they're more likely to run into each other in the walls of the container, leading to an increase in pressure. So let's take a look at what that means. I'm going to reset this. We'll put in 100 gas particles, and we'll take a look at the relationship between pressure and temperature of a gas, which means we have to hold the volume constant. So I'm going to hold the volume constant, which means the box is going to remain the same size. And Gay-Lussac's law says if we increase the temperature of this gas and we give these gas molecules more energy, they're more likely to run into each other inside this container, which means we should see an increase in pressure. So we increase temperature, and we look for the corresponding change in pressure. So that pressure went up to about 4 times up to about 40 atmospheres. So we see the direct relationship between increasing the temperature and an increase in pressure. And the same idea if we were to decrease the temperature, slow down those gas molecules, give them a chance for less collisions, we see a lower pressure due to the lower amount of collisions occurring. Now we'll take a look at a couple examples of Gay-Lussac's law. First one, we have a sample of gas that sits in a room at 303 Kelvin in 1 atmosphere. If we increase the temperature to 403 Kelvin, what is the new pressure exerted by the gas? So first, we want to take a look at, well, we're dealing with a gas and temperatures. We have pressure as well. Well, this is going to be a gas law problem. So let's see what we have. We have a gas sitting in a room at an initial temperature of 303 Kelvin and 1 atmosphere. So our initial pressure is 1 atmosphere. Temperature gets increased, or a changing condition, or T2, becomes 403 Kelvin. Well, and if we have a new pressure, well, we're looking for a new pressure, so that's going to be what we're going to solve for. Now, Gay-Lussac's law says that P1 over T1 equals the quotient of P2 over T2. We are missing the P2 there, so I'm going to plug these in. We have 1 atmosphere, and since we're starting with pressure in atmospheres, we're going to end with a pressure in atmospheres. We don't know the P2. We know that the temperature changes to 403 Kelvin. We cross multiply and divide, and our P2 becomes 1.33 atmospheres. So our increase in temperature led to an increase in pressure. If we wanted to use kPa, we would multiply this by 101.3 kPa, and that would give us an answer of 134 kPa. Both equal values, just using different units, but both representing the same amount of pressure. Now, generally, changes in these different properties of gas, volume, pressure, temperature, are going to happen simultaneously. So this is convenient to combine them into one equation. And this is what we call the combined gas law. And this is what we're going to mainly be using. This is given to you on table T under the combined gas law. Each variable is identified for you here. And for any problems that you're going to see, if you read in the question that something is held constant, let's say a temperature is held constant. So the changing condition doesn't change from beginning to end. We're left with, we can ignore that variable that's held constant. What we're left with is Boyle's law. P1 V1 equals P2 V2. Sometimes we'll see them where we need all 6 of these here. Sometimes we're just going to need 4. Depends on the type of problem. So we're going to have to kind of whittle it down. Now, units for both pressures have to be the same, atmospheres or kilopascals, and we have to make sure that our temperature is always in Kelvin. So we have to convert that if it is not in Kelvin. I'll do a couple examples here. We're going to have to define a few more variables when we combine these all together, but we'll approach it the same way. So we have a 2-liter sample of gas at STP. It's heated to 500 Kelvin and compressed to 200 kPa. What is the new volume of the gas? Now, our combined gas law has 6 variables in it, and we're going to have to figure out which one of these we are going to want to solve for. Now we have a 2-liter sample of gas. So our initial volume is 2 liters, indicated by the L, at STP, standard temperature and pressure. Standard temperature is 273 Kelvin, and standard pressure is 101.3 kPa. And I'm choosing kPa because we already have a value here of 200 kPa for the changing pressure. And we're going to have to convert one of those numbers. If you wanted to use atmospheres, you'd have to convert kPa. Otherwise, we can leave it just as is. Now we're looking for the new volume of the gas. That's what the question is asking us for. So we need change temperature, which is 500 Kelvin. Now we have 5 out of our 6 variables, so we can use the combined gas law to solve for that new volume of the gas after exposed to these changing conditions of being heated to 500 Kelvin and increasing the pressure to 200 kPa from 101.3, so almost doubling that pressure. So we're going to solve for the V2. We'll plug each of these in. We have 101.3 kPa, 2.00 liters over 273 Kelvin equal to 200 kPa. The V2, which we're going to solve for, and our changed temperature of 500 Kelvin. Now this comes out to, after we cross multiply, and we're left with units, and I want you to see this, of Kelvin times kPa times liters, and that is equal to 54,600 Kelvin times kPa, and our V2. Now what we do here is divide this, and just so you can kind of see what's happening with our units, these are canceling. We're going to do the same thing here. kPa cancels, K cancels, we divide our number there, and we're left with liters. So our new volume in liters, sticking with 3 significant figures, is 1.86 liters. Careful with your math. Make sure you fill in on paper first what you're plugging into, and then punch it into your calculator. We'll do one more practice problem here. Again, feel free to stop the video, attempt the problem, and check your work. So we have a half-liter sample of gas at STP that's heated to 373 Kelvin and compressed to 150 kPa. What is the new volume of the gas? Now, determining that this is a combined gas law problem, we're going to see what variables of the combined gas law we have. And that's going to be P1 V1 over T1 equals P2 V2 over T2. So we have a half-liter sample of gas, starting condition, at STP. And I'll use 101.3 kPa for the standard pressure, and standard temperature will be 273 Kelvin. Now it gets heated to 373 Kelvin. And we see that it's compressed to 150 kPa. What is the new volume of the gas? So we'll plug each of these in to our combined gas law. We're solving for the V2. The V2 comes out, maintaining significant figures, as 0.461 liters. If you guys have any questions, make sure you write them down and come and see me and get your questions answered. Hope you guys have a great day.